Good morning, my dear students. In our previous video, we have already started a new chapter of class 12, that is electric potential and capacitance. And some of the important concepts also we discussed in previous video, and they are electric potential difference, and electric potential energy. And at the end of the video, we derived one important derivation also, and that is electric potential due to a point charge. Okay, and that derivation was V is equal to 1 divided by 4 pi epsilon naught Q divided by R. Okay, so this was the derivation. Here R indicates what? It is distance between source charge and the point where we are supposed to calculate electric potential. Okay, suppose if this is a source charge, okay, in this case it is Q. Okay, actually you can take it as Q. Okay, and if it is source charge at a particular point, say it is point P at a distance R from the source charge. If you want to calculate electric potential at point P from the source charge at a distance of R, then the formula is going to be V is equal to 1 divided by 4 pi epsilon naught Q divided by R. Okay, and as you can observe, the electric field at point P is going to be, we have already calculated this also, E is equal to 1 divided by 4 pi epsilon naught, it is Q divided by R square. Okay, see, electric potential is also depending on R, electric field is also depending on distance R. Okay, but these two are depending inversely, but electric field is square of inverse and the electric potential is just inverse of distance. Okay, and there is a difference actually. E is inversely proportional to square of distance and V is inversely proportional to just distance. Okay, it means electric field intensity is going to decrease more rapidly than electric potential. Okay, if we draw the graph between the electric field and distance, or electric potential and distance, these two vary with distance actually, and the graph is going to be like this. See, this is V or it is E. Okay, and this is going to be R. And see here, and this is going to be, okay, and this graph is going to be electric field graph, electric potential graph. V is equal to, V is inversely proportional to R, and this is going to be electric field graph. E is inversely proportional to square of distance. Okay, as you can observe, electric field graph is decreasing more faster, okay, than electric potential graph. It means electric field is going to decrease more rapidly, okay, more faster than the electric potential. Okay, and this was electric potential due to point charge, and this was very important derivation which we derived in our previous video. And this is for a point charge. Okay, if there are many charges, okay, system of charges are there, then the formula is going to be different. You can observe here. See, if this is, let us consider a point P, okay, and this is one charge Q1, this is another charge Q2, this is Q3, which are located at certain distances R1, R2, R3, and this is Q4, okay, which is located at a distance of R4 from point P. If I are asked to calculate electric potential at point P due to all these charges or system of charges, then the electric potential formula is going to is equal to electric potential at point P due to all the charges Q1, Q2, Q3 and Q4, that is 1 divided by 4 pi epsilon naught Q1 divided by R1 plus 1 by 4 pi epsilon naught Q2 divided by R2 plus 1 divided by 4 pi epsilon naught Q3 divided by R3 plus 1 divided by 4 pi epsilon naught Q4 divided by R4. If n number of charges are there, then no problem, you can go on adding. Okay, and please do remember, we have considered all the charges as positive. Therefore, I have considered only plus Q1 plus Q2 plus Q3 plus Q4 like that. If these charges are given in negative, then the formula is going to be minus Q1 minus Q2 minus Q3 minus Q4 like that. Or you can consider one more charge here like this. It is minus Q5, okay, which is located at a distance of R5. Then it is going to be plus 1 divided by 4 pi epsilon naught minus Q5 divided by R5. I have considered here minus Q5 actually. The reason is electric potential is a scalar quantity which is having only magnitude and it has no direction. Therefore, the magnitude of this charge is minus Q5. Therefore, I have written minus Q5. Okay. Since it has no direction, therefore we can just add by algebraic method. Okay. And what is common in all? It is 1 divided by 4 pi epsilon naught. And inside the bracket, it is going to be Q1 divided by R1, Q2 divided by R2, Q3 divided by R3 plus Q4 divided by R4 minus Q5 divided by R5. Okay, so this is electric potential at point P due to all the charges. Okay, for a system of charges, okay, so this is the formula. Okay, if there are n number of charges, then your addition is going to continue like this: Qn divided by Rn. Okay, if there are n number of charges. Okay, and in this case there are only 5 charges are there. Therefore, we have to finish our formula here. Okay. Okay, next we shall take up our next discussion: electric potential due to dipole. Okay, as we have calculated electric field due to dipole, and now we shall calculate electric potential due to dipole. Electric potential due to dipole. Okay, dipole is a pair of charges separated by a pair of opposite charges separated by a small distance, a finite distance. Okay, see here, first we shall calculate on axial line of dipole. And please do remember, my dear students, that is the electric potential formula is V is equal to 1 divided by 4 pi epsilon naught Q divided by R, where this Q is source charge and R is what? It is distance between the charge and the location where we are supposed to calculate electric potential. Okay, so consider one dipole like this. This is minus Q and this is plus Q. The direction of electric dipole moment is from negative to positive, and this is center of the dipole. This distance is L, this distance is L, and the total distance is 2L. Okay. Okay, let us consider a point P at a certain distance. Okay, from the center of dipole we shall consider a point P at a distance R. Okay, this point P is at R distance from the center of dipole. Okay, then this distance from center of dipole, point P is R distance, and from plus Q the distance is going to be, total is R and this is L, therefore it is R minus L. Okay, so the distance between plus Q and point P, it is how much? It is R minus L. R minus L. Okay, and the distance between minus Q and P is how much? It is going to be from here to here, this distance is R, and from here to here it is L. Therefore, R plus L is distance between minus Q and P. So this is R plus L. Okay. Okay. Now, electric potential due to plus q charge. That is V due to plus q is equal to 1 divided by 4 pi epsilon naught q divided by r is there, and in place of r I am supposed to write r minus L, because this distance is distance between charge and the point where we are supposed to calculate potential, and in this case this is the charge plus q and the distance is r minus L, because at this point we are supposed to calculate electric potential. Okay, and now let us call it as 1. Electric potential due to minus q charge, and V due to minus q is equal to 1 divided by 4 pi epsilon naught minus q divided by r plus L. As you can observe here, this minus q and point P, they have a distance how much? R plus L. And I have put a negative sign here because the electric potential is a scalar quantity. Okay, therefore you have to consider its polarity also. And the total potential, net potential at point P, it is going to be V net is equal to V due to plus q plus V due to minus q. Okay, total potential is equal to V due to plus q, V due to minus q. Therefore V net is equal to 1 divided by 4 pi epsilon naught q divided by r minus L and plus 1 divided by 4 pi epsilon naught minus q divided by r plus L. Okay, in these two what is common? 1 divided by 4 pi epsilon naught, and even q is also common, and inside the bracket 1 divided by r minus L minus 1 divided by r plus L. Okay, and V net is equal to q divided by 4 pi epsilon naught r plus L minus r plus L divided by r square minus L square, because it is in the form of a plus b, a minus b. Okay, therefore here minus r plus r cancel, so L plus L is 2L. So what is remaining? Q into 2L divided by 4 pi epsilon naught r square minus L square. Okay, so this is V net, and as you know, Q into 2L, the product of magnitude of either of the charge and the distance between them is called as what? Dipole moment. Okay, so it is 1 divided by 4 pi epsilon naught P divided by r square minus L square. This is V net, electric potential at point P, okay, on the axial line of dipole. This is the formula. And as you can observe, this r is very large compared to L, because L distance is very small distance compared to r. If we neglect this L, then the formula is going to be V net is equal to 1 divided by 4 pi epsilon naught P divided by r square minus L square. Okay, so I am going to write here V is equal to 1 divided by 4 pi epsilon naught P divided by r square. This is the formula. Okay, if we considered r as greater than L, then this is the formula. This is electric potential due to point charge, and this is electric potential due to dipole on axial line. Okay, here also electric potential is decreasing, because electric potential is inversely proportional to square of distance, therefore electric potential go on decreasing on an axial line of dipole. Okay. Okay, now second case, electric potential on an equatorial line of dipole. Second case, that is equatorial line. Equatorial line of dipole. Okay, so for this, once again consider one dipole. This is minus q, this is plus q. Separation is how much? It is 2l. Okay, and equatorial line, a line passing perpendicular to the dipole. Okay, and let us consider this point as P. At point P, we are supposed to calculate electric potential due to minus q and plus q, and this point P is at a distance of r from the center of dipole. Okay, distance we have considered from the center of the dipole only, because in order to make the derivation easy, we have considered in axial line also we considered the distance, okay, r from the center of dipole, and here also it is from center of dipole. And now we should know this distance, okay, and this distance. And you know this distance is r, this distance is l, and this is going to be according to Pythagoras principle under root r square plus l square, and this is also under root r square plus l square. Okay, and at point P, due to minus q the potential, and at point P due to plus q potential we are supposed to calculate. Okay, let us begin our derivation. Electric potential at P due to minus q. Okay, that is V due to minus q is equal to 1 divided by 4 pi epsilon naught minus q divided by under root r square plus l square. Let us call it as equation 1. And the electric potential at P due to plus q, that is V due to plus q is equal to 1 divided by 4 pi epsilon naught plus q divided by under root r square plus l square. This is 2. Okay, and now electric potential, total electric potential due to dipole, that is V net. V net at P. Okay, that is V net is equal to V due to plus q minus, sorry, plus V due to minus q, and V due to plus q is how much? It is 1 divided by 4 pi epsilon naught q divided by under root r square plus l square, and V due to minus q is, since here it is minus is there, therefore plus into minus is minus 1 divided by 4 pi epsilon naught q divided by under root r square plus l square. Okay, since both are same and one is positive, one is negative, they cancel each other, therefore V net is going to be 0. It means electric potential due to dipole on an equatorial line is going to be 0. Okay, so remember, this is very important observation. Electric potential due to dipole on an equatorial line, any point on an equatorial line is going to be 0. Okay, electric field was not 0, but electric potential is 0. Okay, okay, I will write here V is equal to 0. This is for equatorial, and this is for axial, and this is for point charge. Okay, and now we shall consider one general case. Okay, not on axial line, not on equatorial line, it is a general case. Okay, we shall calculate electric potential due to dipole on general case, general point. That is third case. This is also very important case. Okay, electric potential on any point other than axial and equatorial. Okay, electric potential on any point due to dipole, due to dipole. So for this, consider one dipole. This is minus q, and this is plus q. Okay, and from the center of dipole, okay, at a distance of r, okay, let us consider a point P where we are interested to calculate electric potential, and let us name the dipole as A and B, and center of the dipole is O. This distance we know it is L, and this distance also we know it is L, because the separation of dipole is 2L. Okay, and this point P is at a distance of how much? It is BP. Okay, this distance we should know, and this distance it is AP. Okay, we should know AP distance and BP distance. Okay, and the dipole is that point P is at an angle of theta. Okay, and if this distance r and this distance L, we should know BP distance. Okay, we shall do one thing, we shall draw a perpendicular on OP. Okay, now this point is C. You can observe here PC distance and BP distance both are same. PC distance and BP distance both are same. If we know PC distance, then certainly BP is going to be same. Okay, therefore we should know PC distance. Okay, and as you can observe, this angle is theta. Okay, and this is 90 degree. Therefore I can write it as from a right angle triangle OCB, cos theta is equal to base divided by hypotenuse. Base is what? It is OC, and hypotenuse is OB. Okay, and OC is equal to OB cos theta. OB is how much? It is L, and it is cos theta. Therefore OC distance we know it is L cos theta. OC distance, this is what? It is L cos theta. And the total distance we know OP is equal to what? It is R. Therefore CP or PC is equal to, we can write PC is equal to OP minus OC. Okay, OC, and OP distance is how much? OP distance is R. From here to here this distance is R, and OC is how much? It is L cos theta. Okay, therefore PC is equal to what? It is R minus L cos theta. I can write here R minus L cos theta. Okay, so therefore now I know this distance, this is R minus L cos theta. Okay, and similarly I will extend this line. Okay, and I will draw a perpendicular from point A on this line, PO line. Okay, and let us call it as D. Okay, once again this is 90 degree. If this is angle theta, this is also angle theta. Okay, therefore I can write this as it is going to be L cos theta once again. Okay, and see here AP and PD both are same. AP is equal to it is PD. Okay, and PD is equal to, I can write it as PO plus OD. PO plus OD. PO is how much? It is R, and OD is how much? It is L cos theta. Therefore AP is equal to how much? It is R plus L cos theta. So this distance is R plus L cos theta. Okay, and this distance is R minus L cos theta. Okay, so I will remove this. Okay, and this distance was, it is R minus L cos theta. Okay, and now we shall begin our derivation. Electric potential due to positive charge is equal to 1 divided by 4 pi epsilon naught Q divided by R. Q divided by R is there, and in place of R I am supposed to write this is R minus L cos theta. R minus L cos theta. Okay, and electric potential due to minus Q charge is equal to 1 divided by 4 pi epsilon naught minus Q divided by this minus Q and P point, they are separated with a distance how much? R plus L cos theta. So it is R plus L cos theta. Okay. Therefore, total potential at P, V net or V total potential is equal to V due to plus Q plus V due to minus Q. Therefore, V net is equal to, okay, in both these, what is common? 1 divided by 4 pi epsilon naught is common, and inside the bracket Q is also common actually, and 1 divided by R minus L cos theta minus 1 divided by R plus L cos theta. This is what remains. Okay, and I can write it as Q divided by 4 pi epsilon naught, okay, R plus L cos theta minus R plus L cos theta divided by A square minus B square, A plus B, A minus B, it is in the form. Therefore, I can write it as R square minus L square cos square theta. Okay. And as you can observe here, R is cancelled. What is remaining? L cos theta. L cos theta is, it is 2L cos theta, and R square minus L square cos square theta is there. Okay. As you compare L and R, okay, L and R is going to be larger than L. Therefore, if I neglect L or if I consider L as 0, this quantity is going to be 0. Okay. If I consider R as greater than L, then L square cos square theta is there. If I consider L as 0, then 0 into anything is 0. Therefore, in the denominator, what is going to remain? R is going to remain. Therefore, V net is equal to Q divided by 4 pi epsilon naught 2L cos theta divided by R square. Okay. And Q into 2L, the product of magnitude of either of charge and the separation between the charges is called as what? It is dipole. Therefore, Q into 2L, I can write it as P. Therefore, it is going to be 1 divided by 4 pi epsilon naught P cos theta divided by R square. This is V net. So, total electric potential at point P, okay, is going to be 1 by 4 pi epsilon naught P cos theta divided by R square. Okay, and one point remember, if I considered equatorial line, then theta is going to be 90. Okay, because this is dipole, and if I consider equatorial line, then the theta is going to be 90 degree. See here, this is dipole and this is equatorial line. The angle is going to be 90 degree. Okay, and cos 90 is how much? 0. 0 into anything is 0. Therefore, V net is equal to 0. It means if I consider any point on an equatorial line of the dipole, the potential is going to be 0. Okay, or if I consider axial line means this line. Okay, this line means the dipole is having how much angle? 0 degree. Okay, therefore cos 0 is 1. Then the formula is going to be V net is equal to 1 by 4 pi epsilon naught P divided by R square. P divided by R square. Therefore, this is a formula for axial line and this is formula for equatorial line. Okay, equatorial line has 0 potential, no need to calculate. I will write here V is equal to 1 by 4 pi epsilon naught P cos theta divided by R square. This is any point. Okay, any point due to dipole. Okay, so this is all about electric potential due to axial line, okay, equatorial line and general case. Okay. Now we shall start one more important derivation, and that is relation between electric field intensity and electric potential. This is very important derivation because this has appeared in final examination many times. Okay, so now relation between E and V. where E is electric field intensity and V is electric potential. Remember, electric field intensity is a vector quantity and V is potential. Electric potential is a scalar quantity. Okay. So for this, consider a charge, source charge plus Q, and it has a direction of electric field like this, radially outward, since it is a positive charge. Okay. And this is the direction of electric field. At point A, consider one test charge. This small q is a test charge located at a point A. Okay. Now what you do is, you displace this plus q charge, test charge, okay, in this direction, okay, opposite to the direction of electric field. You apply some external force and you displace, okay, to a point B. Okay. See, this distance AB distance is a very small distance. These 2 points are very close to each other. The distance between them is very negligible. Okay. Then and then only I can treat the electric field intensity between A and B as uniform. Okay, this is a very small distance and this charge is been displaced, okay, from A to B. Okay. And at this point, okay, this charge is experiencing a force due to electric field, and that force is F is equal to Q into E in the direction of electric field. Force due to field, that is F is equal to QE, okay, in the direction of field. Okay, the force due to plus q charge and this charge, source charge, and the electric field, both are in same direction. Okay. Now you have applied some external work and you have displaced the charge, small q charge, from A to B. Okay, and that is force into displacement creates what? Work done. Therefore, work done in displacing the charge, the test charge, from where to where? From A to B. That is W is equal to, since a very small displacement is there, therefore the work done is also going to be small. Therefore dW is equal to F into dr, where what is this F? This is force. What force is this? This is external force. And remember, this external force and force due to electric field, both have to be same. Okay, I will write here F external must be equal to F electric, force due to electric field. They must be equal and they must be opposite. Okay, and in place of external I can write it as F electric minus F electric into dr. dW is equal to, and force due to electric field is what? It is QE. Therefore I can write it as minus QE into dr. dW is equal to, okay, I will bring this Q this side. Therefore it is going to be dW divided by Q is equal to minus E into dr. Okay, where dW is what? Work done in bringing this positive charge, test charge, from where to where? From A to B. And in previous video only we have discussed work done in bringing a unit positive charge from one point to another point is called as what? Electric potential. Therefore in place of dW by Q I can write it as dW by Q is V is equal to, since dW is there, very small amount of work is there, therefore potential is going to be very small. Therefore I will write it as dV is equal to minus E into dr. Therefore E is equal to minus dV divided by dr. A very very important observation, that is electric field intensity is equal to minus dV divided by dr. This negative sign indicates what? Change in potential. Okay, with distance is opposite to the direction of electric field. Understood? So I will write here negative sign indicates the change in potential because dV is a change in potential. Okay, change in potential with distance is opposite to the direction of electric field intensity. So some important points regarding this derivation. See here, E is equal to minus dV divided by dr. Okay, dV is what? Change in potential. Okay, negative sign is there, therefore I will write negative sign, divided by dr. Dr is what? Distance. And this is E. Two sign shows that first point, the electric field intensity E is in the direction of decrease in potential. It means consider one source charge here, Q. Okay, and let us consider one point A. Okay, we shall place a test charge Q. Okay, and you work, okay, on this test charge in bringing from A point to B point, and at A point the potential is said to be VA and potential at B is going to be VB. As you can observe, this B is very close to Q compared to A. Therefore, potential at B is more than potential at A. That is, VB is greater than VA. Okay. Then decrease in potential is going to be from Q. Okay. As the distance increases, the potential go on decreasing. It means VA minus VB. VA minus VB is what? Change in potential or decrease in potential, and this is the direction of electric field. For example, see here, from this test source charge, if you go away from this source charge, the electric potential go on decreasing. This is the direction of decrease in potential. Okay, from VB to VA the potential is decreasing. From VB to VA the potential is decreasing. Therefore, this is the direction of electric field. Okay, so this is the meaning of this formula. E is equal to dV divided by dr. Okay, and one more point. See, electric field E is equal to dV is there. dV is what? It is potential, and potential has a unit what? Volt. Okay, and dr is what? Meter. Okay, so volt per meter is one more important unit of electric field. Okay, before this, for Newton per coulomb was the unit. Electric field E is equal to F divided by Q. F is Newton and Q is what? Charge. Therefore, Newton per coulomb is unit of charge. There are two units actually for electric field. One is volt per meter, another one is Newton per coulomb.